Pure fission weapons are inherently inefficient. Only a small percentage of the fissile material, typically less than 20%, undergoes fission before the core disassembles due to thermal expansion. This premature disassembly, known as fissile, limits the maximum yield achievable by a simple implosion device. Boosting overcomes this limitation by injecting a massive surge of neutrons precisely at the moment of maximum compression. This technique allows warhead designers to significantly reduce the required mass of plutonium or uranium while maintaining or increasing the explosive yield. The goal is not to initiate the reaction, but to sustain and accelerate it past the point of hydrodynamic disassembly. The boosting agent is a mixture of deuterium and tritium gas stored in a sealed, high-pressure reservoir external to the primary pit. Tritium, a radioactive isotope with a 12.3-year half-life, decays into helium-3, which is a potent neutron poison. Therefore, the gas mixture must be periodically replaced or refurbished to maintain optimal performance. The reservoir uses a specialized valve system, often employing a metal hydride storage bed, ensuring the gas is injected into the hollow center of the plutonium pit, microseconds before the peak of the implosion. This precise timing is critical for maximizing the fusion yield. The conventional explosive lenses surrounding the primary stage generate a spherically converging shock wave. This wave compresses the plutonium or uranium pit to densities exceeding twice that of normal solid state. As the pit compresses, the central void, where the deuterium-tritium gas has been injected, shrinks rapidly. The kinetic energy of the imploding tamper and pusher materials converts into thermal energy, raising the temperature of the central gas mixture dramatically. This process creates the necessary confinement and heating required to initiate the thermonuclear reaction within the core.
Achieving thermonuclear ignition in the deuterium-tritium gas requires simultaneous high density and high temperature. The temperature must exceed 50 million Kelvin, sufficient to overcome the Coulomb barrier between the deuterium and tritium nuclei. At peak compression, the density of the gas can reach several hundred times that of liquid hydrogen. This extreme state, though transient, is sufficient for the deuterium-tritium reaction to proceed, fusing into helium-4 and releasing a high-energy neutron. The reaction rate is highly sensitive to both temperature and density, demanding extremely precise engineering of the implosion system. The deuterium-tritium fusion reaction releases a single neutron carrying 14.1 megaelectronvolts of kinetic energy. This energy is significantly higher than the 2 megaelectronvolts typical of fission neutrons. Crucially, this fusion burst occurs in a frame time measured in tens of nanoseconds, precisely when the fissile core is at its maximum supercritical state. This timing ensures that the maximum number of fissile nuclei are exposed to the high-energy neutron flux before hydrodynamic expansion begins. The sheer quantity and high energy of these neutrons define the effectiveness of the boosting process. The high-energy fusion neutrons are highly effective at inducing fission in both plutonium-239 and uranium-235. A single 14.1 megaelectronvolt neutron can also cause fast fission in uranium-238, which is normally non-fissile with thermal neutrons. Furthermore, these neutrons increase the neutron multiplication factor, K effective, of the core from perhaps 2 to values approaching 5 or 6. This rapid multiplication ensures that a much larger fraction of the fissile material fissions before the core disassembles, boosting the yield by factors of 10 or more compared to an unboosted design.
Boosting allows designers to use smaller amounts of fissile material, often below the theoretical unboosted critical mass, while still achieving reliable yields in the tens of kilotons. This reduction in fissile material is critical for miniaturization, enabling the creation of compact warheads suitable for intercontinental ballistic missile re-entry vehicles. The efficiency gain is measured by the burn-up fraction, which increases from the typical 1 to 2% in unboosted devices to 20 to 40% in boosted primaries. This efficiency is essential for maximizing the payload capacity of modern delivery systems. The first successful boosted fission test was conducted by the United States in 1951 during Operation Greenhouse. Modern warheads universally employ boosting in their primary stages due to its inherent reliability and yield flexibility. This design choice provides consistent performance across a wide range of environmental conditions, including temperature and vibration stresses during deployment.
The precise control over the timing and quantity of the injected deuterium-tritium gas allows for variable yield options, where the explosive power can be tailored based on mission requirements, a capability known as dial-a-yield. Handling and storing tritium presents significant technical challenges due to its radioactivity and tendency to permeate materials, requiring robust containment systems and regular monitoring to prevent environmental release. The necessity of periodic refurbishment due to tritium decay adds complexity to stockpile maintenance. Future boosting concepts explore advanced materials and alternative fusion fuels, such as deuterium-deuterium, although the lower neutron yield makes deuterium-tritium the current standard. The proliferation risk associated with boosting technology lies in its ability to maximize yield from minimal fissile material, complicating international verification efforts.